In Autodesk Simulation Mechanical, you can perform steady-state and transient heat transfer analyses using brick, tetrahedral, plate, and 1D thermal rod type elements. A steady-state analysis provides one set of results indicating the thermal equilibrium state of the model. To determine how the results vary over time, run a transient heat transfer analysis. The available thermal loads are found here. For parts, surfaces, or vertices, you can define initial temperatures or apply controlled temperatures. The latter can be constant or can vary over time using a load curve. You can apply radiation and convection loads to selected surfaces. The ambient temperature, radiation function, and convection coefficient can be constant or time dependent. Optionally, convection coefficients can also be temperature dependent. Use the built-in calculator to determine appropriate convection coefficients based on general parameters, fluid properties, and geometry. Or look up predefined values from the convection coefficient library. You can apply heat source loads to surfaces or vertices. A positive value represents a heat source and a negative value a heat sink. The magnitude can be fixed or time dependent. You can define internal heat generation for parts. The heat output can be constant or can be time or temperature dependent. Additionally, current results from a prior electrostatic analysis can be used to control heat generation to determine the Joule heating effect. Lastly, you can define body-to-body radiation between two or more parts. The view factor and shadowing effects are considered. The ambient temperature within the enclosure can be constant or time dependent. You can specify which surfaces participate and define the emissivity on a per-surface basis. The emissivity can be constant or temperature dependent. Isotropic, orthotropic, and phase change material models are available. For each, the properties can be constant or temperature dependent. For phase change material models, define the latent heat of fusion. During conversion from solid to liquid or liquid to solid, the heat flow changes the state of the material rather than its temperature. This example is a radial fin heatsink mounted atop a silicon semiconductor that generates 15 watts of heat. A convection load is applied to the exposed surfaces of the heatsink assembly, and the ambient temperature is 75 degrees Fahrenheit. Surface contact has been defined between the semiconductor and the heatsink base, and a total contact resistance of 0.6 degrees per watt is included. Contact resistance is necessary for determining realistic temperature differentials across part boundaries. Let's look at the thermal results. You can view the calculated temperatures at each time step or the initial temperature. This animation shows the change in temperature over a 100-second time period after the semiconductor is energized. We'll select the node near the center of the chip and graph the temperature variation over time. Notice how steady-state conditions are achieved after about 90 seconds. Beyond this point, the dissipation of the heatsink and semiconductor are equal, and the temperatures are stable. You can display the heat flux per unit area. Choose to show the magnitude, a vector plot, or the flux components in global or local axis directions. Finally, you can also view the heat flow rate through the element faces.